Hello everyone, welcome back to Exploring Quantum Physics. I'm Charles Clark. We're going to conclude this lecture by a look at some of the current research topics in the area of quantum gases.
Now we're going to look at a few examples of current research in ultra-cold quantum gases. And we just have time for a few topics, but I think you'll see the richness of the field, and by looking at references to these in the open literature, you can find many other interesting ideas. So, first of all, in situ imaging of individual atoms. Now, this differs from the mode that we've been using earlier in this lecture, where we've been discussing atomic absorption images, which don't resolve individual sites. And there's some amazing developments in this area. Another very striking invention, the cold atom scanning probe microscope. So this is something that might be very suitable as an extension of the atomic force microscope, and based on the use of an atomic Bose-Einstein condensate as a tip. And it's not just a concept, it's something that has been implemented. Atomic atom interferometry over very long distances, tens of meters, with flight times of several seconds, that can be used to test the equivalence principle, for example, or do very precise measurements of Earth rotation and the like. And then the optical lattice clock, which had an amazing development reported early in the year 2014, making it then the world's most accurate clock, and also, as we'll see, providing a sort of a laboratory for studying basic quantum many-body physics. So, to the issue of in situ imaging, here's work done by a group of David Weiss at Penn State University. You see three images, and the glowing points within each one of these are individual atoms sitting on the sites of a cubic optical lattice, and the different columns here have the image focused on different interior planes of the lattice. So what you see, if you look at just one of these images, you see the very bright spots. Those are individual atoms, and then there's some fuzzy areas nearby. Those are atoms in a different plane that's defocused from the image. And so you can see that the lattice here is imperfectly and irregularly filled. On the other hand, every glowing point is at an optical lattice site in sort of a regular crystal array. The lower row here is the same system with a photograph taken 3 seconds after the photograph of the upper image. And so with this you can see that there is both stability and change in the lattice. There are many common sites that are occupied in both, and then there are also some changes. So this just shows remarkably how you can get a regular registration of atoms and maintain it over a significant period of time. An even more amazing example involves the creation of an optical lattice inside an electron microscope. And in the lattice sites, there are a rubidium atom is held, and it's fluorescing so that you see the light from the rubidium atoms. And then the electron beam can be swept over this system and selectively ionize the rubidium atoms in certain sites so that you make vacant holes in the lattice where there are no atoms. A remarkable act of precision engineering here. And my colleague noted that the font design is rather elegant as well. This is, of course, the Schrödinger equation. Finally, on this imaging frontier, a tremendous development by Marcus Greiner's group at Harvard called the quantum gas microscope. And here you're seeing an image of ultra-cold atoms, Bose-Einstein condensate, held in an optical lattice with a field of view of 100 microns, a tenth of a millimeter. Very large. And on the right here is another image taken of a smaller region where you can clearly see these individual the signals from individual atoms. If you like this sort of thing, I strongly recommend looking at the videos where you actually see real-time motion of atoms and optical lattices on time scales of fractions of a second. Just fascinating work. And so this is making possible analysis of ultra-cold atom systems at a degree of resolution simply was not possible about 5 years ago. Next topic, cold atom scanning probe microscopes. So here's an artist's conception of an instrument that has been built at the University of Tübingen in Germany, and it compares a so-called cold atom tip, which is just a Bose-Einstein condensate held in a small electromagnetic trap, compared to a traditional atomic force microscope tip. So the AFM, or atomic force microscope, is now a widely used analytical tool for measuring microstructure. The BEC-based concept gives a tip of about the same size, but it is a lot softer, so it can measure surface tip interactions over a greater range than is possible with the standard conventional atomic force microscopy. Here's the reality of that schematic that is shown in the previous figure. Very impressive, reported in Nature Nanotechnology in the year 2011. And this instrument, see here's the length scale, 3 millimeters, consists of a carrier chip, which is here, that can scan a Bose-Einstein condensate back and forth over the sample. And the sample in this case consists of carbon nanotubes that have been grown on the so-called nanochip. And the BEC is scanned over the tubes to generate a signal that tells you something about the topography of the tube. Here is an image from that paper. The sensing mechanism that's used in this instrument is the loss of the atoms from the condensate. So when the condensate is brought near another material system, there are attractive forces that are imposed on the atoms in the condensate, and some of them can leave the condensate. They typically don't get more atoms back in the condensate. And so the method of analysis of the system involves optical absorption imaging to determine the population loss, or that's inverse, the remaining atom fraction. So this is the spatially resolved signal that's been obtained from that instrument. There are many other concepts for this type of scanning probe microscopy, using, for example, spin polarized atoms to detect micromagnetic structure. Another really amazing technical development, long baseline atom interferometry. This is being implemented in Mark Kasovich's group at Stanford University. And here is a schematic. It's basically a large atomic fountain clock where ultra-cold atom samples produced down here. It's subject to some pulses to mix the states in a sort of typical atomic clock scheme. Then it flies up and back about 10 meters. And this system is being successfully commissioned and is designed to test the equivalence principle, that is, whether the inertial mass and the gravitational mass are proportional, or you might say exactly the same, by looking at the differential acceleration of two species. So rubidium-85 and rubidium-87 can be used in this system with very similar optical control because the transition wavelengths are quite close together. So there's another application of the use of isotope shifts in ultra-cold atomic physics. So finally, to conclude, amazing work done recently in advancing the fundamental accuracy of clocks. And as of spring of 2014, this accuracy of a few parts in 10 to the 18th has gone beyond what was done previously in single ion-based clock. The remarkable thing about this instrument is that it's using a many-atom system trapped in an optical lattice, though with minimal multiple occupancy of lattice sites. And it has been characterized in particular by this measurement of the black body radiation shift on the two clock states. This is a very subtle effect, but modern clocks have become so accurate that the determination of the black body radiation effects on atomic transition frequencies has become a major effort in the world, both theoretically and experimentally. Another use for clocks is as sensors, because if you can measure shifts in frequency to very high accuracy, you can determine the effects of environmental influences. So things like magnetometry, accelerometry, gyroscopy, gravity gradiometry are all a good applications area for very high precision clocks. And also fundamental scientific studies. So this is an example of one such use of the optical lattice clock that was discussed just on the previous slide. It's used as a laboratory for understanding some quantum many-body effects associated with interactions between atoms in the clock. So that concludes this very brief survey. There are many other topics that could be raised, but I hope you've captured some of the excitement and interest in this field and seen how it's spawning. Well, it's not really spawning what you would call commercial technologies at the present time, but it certainly has spawned a vast range of improvements in basic measurement techniques, fundamental scientific understanding, and some applications of sensing that are based on new, previously unexplored physical principles. It's all made possible by the ability to cool and trap atoms, prepare them in a deterministic way, and analyze them. And it's a very exciting field of research that I hope you'll keep track of.